Okay, here's Unit 6, Periodicity. Remember on Friday we talked about how this unit we are looking at the periodic table and we are looking for trends and patterns and getting to know it better because, like I said, it is the biggest cheat sheet anyone will ever give you on a test. So, we're going to look a little bit about the history of how it was put together. So the first guy that we're going to talk about is Johann Dobereiner, and he lived in 1817, and so he discovered a pattern between groups of 3 elements, which he called triads, and so that's a big deal. Put a little star by that. Dobereiner is in charge of triads, and here is an example of his groups of 3. So the first group of 3 that he saw was lithium, sodium, and potassium. And this is a modern version of the periodic table. So this is more of like what he noticed is that, oh look, there's these group of 3, and when you average them out, they have the same average nuclear or atomic mass. So lithium, sodium, potassium, calcium, strontium, barium, phosphorus, acetine, antimony, chlorine, bromine, iodine. He noticed that, hey, these 3 guys kind of act very similar, and so he kind of came up with these groups of triads. So as we discovered more elements, about 50 years later, we get to John Newlands, and he came up with the law of octaves. And so by this time, we had more elements discovered, and he saw that every 8th element had similar properties. And so he said this was kind of like music, how every 8th note in music you start over and they sound the same, and we call those octaves. And so that's where the law of octaves came from. And as you will read in The Disappearing Spoon in chapter 3, is that because he compared it to music, a lot of people thought that he was just making up stuff and thought it sounded too cutesy, and so nobody believed him. But here is an example of his arranged elements in octaves. So some of them you can see we don't use those symbols anymore because we changed the name, but this is how every 8 elements then they would change and you would start over a new one. So that was Newlands. The next guy, almost at the same time, was Dmitry Mendeleev, and he was a Russian chemist, and he's the first person to really catch on to the idea of the periodic table. And so he organized the elements by atomic mass, but more importantly, he was in the lab all the time, and so he knew all the elements' different properties. And so not only did he organize it by mass, but also he organized it by properties that he knew certain ones had together. And so kind of like you and the aliens in that lab, you put all the ones that looked the similar together. And so that was how he originally built it. And so the problem today that why we don't use his table is because some elements did not really follow this arrangement. So here's an example of his. And you can tell we're starting to look a little bit better now. We have hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So that kind of looks like ours right now, but you can tell that it is by atomic mass. So manganese and chromium are out of place compared to ours now. And you also notice that he had missing ones. And that he found gaps in his table, and so what he did is he predicted what their atomic mass would be, and he predicted that one day we would discover these elements. And so just like you trying to guess what the alien is going to look like, he guessed what the elements are going to look like. And then 15 years later, when they actually discovered these elements, people were really, really amazed and surprised that this guy 15 years before had predicted almost exactly how much these elements would weigh. So that gave a lot of credibility to his table. But then finally we get to Henry Moseley, and in 1913 he decided to organize them not by atomic mass, but by atomic number, which remember is the number of protons. And so that really took off, because then what he found, like down here, is that it provided a space for all the elements, even the gaps that Mendeleev had. And so this is an example of what his looks like. Still a little bit different. Obviously, we've messed around with it a little bit more, but we still follow the periodic law, which is what he came up with. And it says that the physical and chemical properties of all the elements are periodic functions of their atomic numbers instead of atomic masses. And remember, periodic is anything that happens over and over, like a pendulum on a clock swinging back and forth. That's a periodic function because it happens the same way over and over. And so that means that the properties of the elements depend on their atomic number, and they occur in a pattern over and over. So the first pattern that we're going to look at is atomic radius. Okay, so on Friday, you were given some data and you were asked to graph the atomic radius for given elements. So I want you to think about the trend that you saw for the atomic element trend for atomic radius. So if you went down a column, you should have noticed that the atomic radius increased. But if you went across a row from left to right, you should notice that it decreased. Okay? So think about, from what you know, like the words atomic and the word radius. And if you had to guess, what would you say atomic radius is? Okay, well, you should know that the radius is the distance from the center of a circle to the outside. So atomic radius is going to be the radius of an atom, or the distance from the center of the nucleus to the outermost energy level, or basically the last electron. And that's going to be the atomic radius right here. So technically, when we measure atomic radius, we take the total distance between two of the same element bonded together, and then we take this whole distance, which is technically 1r, and then 2r, and we divide it by 2. And it's easier for us to do that. But anyway, that's atomic radius. So what we find is on the periodic table, as you move this way, atomic radius is increasing. And then as you move down, it also increases. So on your periodic table that you're supposed to take notes on, I would probably draw an arrow showing that atomic radius is going to increase going to the left and increase going down. So here's a graphic representation. You can see the little spheres, the atomic atoms are getting bigger as you go this way, and then they get bigger as you go down, just like the aliens get bigger as you go down. So this makes sense, right? Because if you're going down, the masses are getting bigger. Every row that you go down, the masses get a lot bigger. But does it make sense that doesn't the mass increase this way too? And does it make sense that as you get bigger masses, they actually get smaller? And then all of a sudden, once they hit here, then they get really big again. So we're going to talk about that on Monday, why that actually happens, because it's a little bit counterintuitive that they would actually get bigger as you go smaller this way, but they get bigger this way. So just remember that the atomic radius increases down and increases to the left. So here is a fancy 3D model bar graph showing the atomic radius. So you can see that down here they're really short, and then it goes up just like a stair step, and then it goes up this way. And so the biggest radius is going to be down here next to cesium and rubidium and francium and all those guys. Okay, so the next thing is ionic radii. Radii is just plural for radius. So for ionic, we need to talk about valence electrons first. And a valence electron is an electron in the highest energy level of an atom. So they're the last electrons on the very outside of an atom. And it means it's the highest S and P sublevels, which we will talk about more on Monday. Okay, and then an ion, as we will learn, is going to be an atom that has a positive or negative charge. So anytime you hear the word ion or ionic, all it means is charged atoms. And again, it's one of those words that science fiction people use a lot, or you hear tossed around a lot to make things seem fancy, but all an ion is a charged atom. So if you rub a balloon on your head and it gets static electricity, you just created ions. Great. So how do you make a negative or a positive charge? Well, that means you have to move around electrons. And so that's why we talked about valence electrons, because they're the ones on the outside. And so you have to lose or gain valence electrons to make ions. So if you gain or lose an electron, that is going to give you a positive or negative charge. So let's look at which one is which. So first one is cations, and cations are positive ions, and that means they have lost electrons. Remember, electrons are negative, so if you lose a bunch of negative stuff, then you are going to become more positive. And an easy way to remember this is that cations are positive because cats have paws. Please never spell positive that way, but you can if it helps you remember, but in English class, please never do that. I will get yelled at. So, if you are positive, a cation, and it means that you lost an electrons, that's going to mean that your radius is going to shrink because you lost electrons. So that will make you smaller than a normal neutral atom. Okay, and then as far as elements go, if you are a metal, usually metals are the only ones that form cations. So everything from lithium to calcium to iron to lead to silver and gold, they form cations. They lose electrons and they become positive. Okay, if you're not though, like let's say you're oxygen, which is not a metal, that means you are more likely to form an anion. Okay, so anions are negatively charged atoms that have gained electrons. Again, electrons are negative, so if you get more electrons, then you become negative. And a good way to remember that is anion is a negative ion. Anion. A negative ion. And then if you gain electrons and you get bigger and fatter, then guess what? Your radius is also going to be larger. So anions are larger than a neutral atom because they gained electrons. Okay? Cations are smaller because they lost weight, they lost electrons. Anions are fat because they ate too many electrons and now they're chunky. Okay, and then if metals usually form cations, then non-metals usually form anions. So it's pretty logical. Okay, so that's all that's in this video. Remember that on Monday and Tuesday, you have your periodic table worksheet due. Just color them in, fill it out, and you'll be good. You have these video notes. Probably will be a quiz, wink, wink. And I also want you to bring a cationic attitude. And if you don't remember that, 1, it's right there. 2, you can go back a couple slides and look. So have a great weekend. I will see you then.